Dr. Jake Lane is going to stand in for Richard Hull. I don't envy you presenting somebody else's slides, Jacob, so thank you very much. I should probably just briefly mention who Richard Hull is and Jake. So Richard Hull is a professor of chemistry and bioscience at the University of Central Lancashire. But Jake is also a visiting UCLan, that's University of Central Lancashire researcher. So he's well qualified to give this presentation. We'll be hearing more from Jake separately in his own presentation later today. But Jake, thank you so much for stepping in.
That's quite all right. Can everyone see that, just to make sure? Yeah, great. Okay, so Richard's talk was all about fire retardants, fire safety, and also then touching there on the circular economy towards the end. So just, if you want to read more about Richard, there's some links there. I think the most important thing to say is Richard is really highly respected within the UK's fire community, and in 2018 he was, along with his colleague Anna Steck, was a member of the expert witnesses that were in the Grenfell Tower inquiry. So they don't just look at furniture, they look at a much wider range of fire and fire hazards. So the outline of this talk is we're going to cover flame retardants, look at why some flame retardants produce more toxic smoke than others, how some flame retardants also can be persistent, bioaccumulative and toxic. The ability, when added to flammable plastics, flame retardants suppress ignition, but they don't prevent burning, as we've already seen. And then finally, all flame retardants prevent some meaningful end-of-life processing. And these slides can be shared at the end of this presentation. So if we start off with just looking at fire deaths in the UK, what we see here is that from when they first started recording fire deaths, we see that fire deaths increased rapidly from the 1950s through to the 1970s. And this is generally put down to more synthetic polymers and materials coming into the home. Then there's a plateauing as fire safety generally becomes more aware, technology starts to catch up. And some would say fire retardants start to get introduced into the home. And then finally, we start seeing this decrease from the late 1980s to present day. And that is due to a variety of factors, not just flame retardants, but also technologies such as smoke detectors becoming a lot more prevalent in the home. And one of the most important things actually really to take away from this slide is that when we look at the causes of these deaths, so early on what we're seeing is that a lot of the deaths are being attributed to burns compared to in smoke inhalation. And then as more and more of these synthetic polymers are coming into the home, and then flame retardants, we're seeing this shift from burns being the biggest cause of fire fatality to toxic gases. And Richard's very kindly just sort of framed that there for you to see a little bit more clearly. So really the take-home message here is that plastics and flame retardant use from the 1970s means that smoke has become the largest killer in household fires. So how are flame retardants toxic? So there is this work that Stuart does that looks at the release of polymers, the release of flame retardants from polymers during their normal use, and then the flame retardant in its in that form is toxic and how that gets into the environment. This also can occur when flame retardants are burnt in a fire. They don't necessarily get burnt and there's a little bit of release, but that's quite rare. What a lot of Richard's focus and our focus within UCLAN is actually on what happens to the flame retardant and how it influences the smoke and the smoke toxicity. And what we see is that the use of flame retardants really can increase that smoke toxicity by increasing the amount of incomplete combustion products that are occurring in a fire, such as carbon monoxide and hydrogen cyanide. So if we take a step back and then just think about flame retardants and how much is globally consumed of flame retardants, what we see is that aluminium hydroxide is the most commonly used flame retardant, accounting for about 38% of all flame retardant usage. But the ones we're most interested in terms of furniture and furnishings is the organophosphorus, the chlorinated and the brominated flame retardants. And in between the chlorinated and brominated flame retardants, we have antimony oxides. These are a group of flame retardant additives that in their own right don't actually have any flame retarding or have very little flame retarding properties. What they do is they allow the reactive species within chlorinated and brominated flame retardants to exist for longer in the flame. So actually what we can say here is that almost 30% of all flame retardants that go into products every year are related to or to aid the use of halogenated flame retardants. So when we talk about flame retardants, it's quite easy to talk. It's quite easy to get confused about what we're talking about. All flame retardants work by reducing the flammability of a product, of a component or a product. What we traditionally think of as flame retardants, and what we're probably talking a lot about today, are gas phase flame retardants. And these are flame retardants that reduce the flammability of a product by interfering with the chemical reaction of the flame. There are other flame retardants on the market that work within the condensed phase, and these primarily focus on reducing the three pillars of the fire triangle. So focusing on the heat, the fuel, and the oxygen, but predominantly on the heat and the fuel. So mineral fillers will release water to reduce the heat that's being exposed to the fuel. Char formers and barrier layers are going to protect that the fuel from that heat source as well. So why a gas phase? So let's first look at gas phase flame retardants. And in order for a gas phase flame retardant to work, they must be volatile enough to interfere with those flaming reactions. This means that they tend to leach out of the polymer because they've got to be volatile, they've got to be able to move. But because they're reacting with the flame, they're also going to produce lots of smoke because they're wanting to cause incomplete combustion, and then incomplete combustion in itself produces more harmful toxic gases such as carbon monoxide and hydrogen cyanide. Due to the chemistry of these flame retardants as well, they're often shown to be persistent, bioaccumulative, and toxic to the environment and to humans. And that in itself is down to their chemical nature. So particularly if we look at halogenated flame retardants, they all have these bonds of a carbon to some sort of halogen, whether it's bromine or chlorine. And these very rarely exist in nature. So there's no way that nature hasn't found a way to break them down. So when they leach out into the environment, nothing's going to stop them from just bioaccumulating. They're also fat soluble. So they'll, once they get into fatty tissues, they're going to start building up there, where they can then have endocrine disrupting properties and other toxic properties. Finally, as I mentioned earlier, they are often used in conjunction with antimony oxide, which is a synergist, and antimony can be extremely poisonous. In fact, it's as poisonous as arsenic. So the environmental impact of halogenated flame retardants has been known about for quite some time, and regulation has always tried to move to ban them, but there is a myriad of chemicals out there for industry to be able to jump on to the next. So there's this history of what we call regrettable substitution, where one chemical is banned only for a new one to come onto the market where there hasn't been any research done on it yet. Then it takes a while for that documented research to be able to build up to show that that similar chemistry of it is having an effect onto the environment and on human health. And then it gets banned, and this cycle continues. One way that industry have started to think about how they can stop the leaching of flame retardants into the environment is by actually putting the flame retardant into the plastic itself. So an example of this is polystyrene, where they have put the bromine groups actually into the backbone of the plastic. This allows them to meet the fire regulation, meet higher fire standards, but you're still going to get that increased smoke and toxicity because it's still using that gas phase flame retardant technology. They also unfortunately break down under UV light, and there is no way of recycling these materials at end of life currently. The other problem family that we're seeing at the moment is the chloral alkyl phosphates. So these are TCEP, TCPP, and TCIPP. There was a study published last year by the National Toxicology Program in the States that showed that all of these have a high likelihood of being carcinogenic to humans, yet they are TCPP and TCIPP are commonly used in flame retardants within furniture. TDCPP, which is this one on the right-hand side, was shown to be mutagenic and subsequently banned from children's nightwear back in 1978. So are flame retardants effective in preventing fires? This is a study that was...
Sorry, just to interrupt, I'm going to have to ask you to wrap up in the next few minutes.
Okay, not a problem. Yeah.
Thank you.
So this study was done with IKEA furniture purchased from the UK and Germany, carried out by Edinburgh University. And they did they put a bin they did a bin fire next to identical pieces of furniture bought from the two countries. So under the UK's regulations and under Germany's, see that the fire takes place, it grows, it overwhelms the fire retardant technologies that are in the UK's furniture, and ultimately you end up with exactly the same scenario. Yeah, there's more toxic gases being released from that UK furniture. Condensed phase flame retardants, broadly, there's three categories: those monofillers, char formers, and barrier formers. Some of these are perfectly safe as a in their native state, so they're actually even E numbers. You'll find them in food. and they're mostly involatile, so they won't get released during the product lifetime, but they can impact end-of-life processing. So unlike metals, all plastics, when they get recycled, they degrade. The chain length of them just breaks down. All these, and actually the fire retardants interfere with this end-of-life processing, because if they just go into landfill, they're just going to leach out and contaminate. If they get into the recycled feedstock, they can contaminate and reduce the quality of that recycler. And then finally, to facilitate a circular economy, fire retardants should only be used in recycling if recycling is possible, and we should be persuading manufacturers to use less flame retardant polymers or metals. So in summary, there are many different types of flame retardants. All are more expensive than the host polymer that is used, and they're only in there to meet regulatory requirements. Fire retardants enable plastics to be used in high-risk situations. Flame retardants are the most effective way in suppressing ignition and early fire growth, but not preventing the fire burning once the fire has grown. Gas-phase flame retardants increase smoke toxicity. Fire safety benefit of flame retardants is questionable, and some flame retardants can leach out of the polymer, and many have been shown to be persistent, bioaccumulative, and toxic. All flame retardants cause problems at end of life. I think that is that.
Well done, Jake. That was really clear and really well presented. Thank you so much.